Hello everyone, welcome to the lecture series on computer vision, and for today's discussion we have here texture. So what is this texture and what is its significance in the classification problems? Texture is defined as it is a group of pixels repeating periodically or aperiodically is said to possess a texture where similar structures are repeated over and over again in the given image. So let's take this as an example. This is my image. So I do have here a structure. So this structure is repeated many number of times in the image. So this structure is nothing but it is composing or it is wrapping a many number of pixels. So these pixels are repeated periodically as well as aperiodically. That means this region I am going to call it is a texture here. That is, texture is a repeating pattern of local variations in the image. So this local variation is being repeated many number of times. So some more examples also is present in this slide. So this is the local variations which are repeated many number of times. Here you can see, here also you can see, and in this image also you can find out the local variations are repeated here many number of times, right? Okay. So this texture provides information in the spatial arrangement of colors or intensities in an image. So the texture is providing some information which may be of color or which may be of some kind of an shape or which may be of kind of an intensity. So this texture is providing to a viewer here. So texture cannot be defined for a point. As I have said you, texture is nothing but it is some kind of a group of pixels, right? This texture which is consisting of a texture primitives, that means some basic elements or texture elements I could call as texels. Like in the pixels, how we are going to call in the similar manner, the texture is having the basic primitive or an element, we call them as a texels here. So this is one texel, this is one texel. These texels are being repeated periodically in a given input image. So that means the texture, like if I am having a uniform image in this manner, so I cannot able to find out what is the texture, because all the intensities in this given image are spreaded uniformly, where I cannot even I cannot able to find out any pattern or anything inside this image. So this image doesn't possess any texture here, texture property, right? So the texture is consisting of a texture primitives or elements. These are nothing but these are the texels. So texture is a repeating pattern of a variations in an image, right? Then how to analyze a given texture? So the texture can be analyzed by, that means we do have here 4 issues in texture analysis. One is a classification, next is segmentation, synthesis, followed with the shape recovery from the texture. So how this texture is helpful in the classification or segmentation, synthesis, and how one can able to recover the shape from a given texture in the image. So let us discuss about the texture classification. So it is concerned with identifying a given texture region from a given set of texture classes. Let me take this one as an example. This is one texture class, this is one texture class, and this is also one texture class. And the same thing, that means it is a family of aluminium foil. So these 3 images are the family of aluminium foil, and these 3 textures or these 3 images, that means these inside these images I do have a textures. These textures are repeated many number of times inside these images. So these 3 images forms a family of linen. Now, so that means these 2 are given to a training phase. That means inside my training phase I am having, so from these input images I extract features from the input images and some kind of a processing is done, and these images are trained here. So finally there's some kind of a like feature vectors I can able to generate by the training phase. Now if suddenly I have been given or provided with some unrecognized or unknown image, so this image is having definitely some kind of a textures in it which are repeated many number of times periodically. Some pattern is repeated, so the texels are repeated inside this image. So what I will be doing, I just do the feature extraction process, and from that some kind of processing and again feature vectors, and after that one these are compared with already existing database feature vectors. So after the comparison I can able to recognize what is this the one that I have been given as a testing image. So what is this testing image here? What is the texture that is present in the testing image? So whether it is my aluminum foil or whether it comes under the family of a linen. So it is the texture classification here is concerned with identifying a given textured region from a given set of texture classes, because these are my texture classes here, from which I can able to recognize what is the input given input textured region, whether it is an aluminum foil or whether it is a linen here, linen family. So each of these regions, each of these regions have unique texture characteristics, because this is having its own texture characteristics, right? Because the shape as you are seeing here, it is giving me some feel, and this image is also giving me some other feel. That means two different or unique texture characteristics I can able to produce from these two families of images. So for this one, in order to find out what the input image texture belongs to which category or family, I am having here some statistical methods, so by which I can able to classify. So there are GLCM, contrast, entropy and homogeneity. These statistical measures I can use in order to classify the given texture image inside the image. Okay. The next one in the texture analysis we do have here is texture segmentation. It is basically concerned with determining the boundaries between the various textures that are present inside an image. So inside my image I do have two families of flowers. One is yellow flower and one is a pink color family of flowers. So both these both are different regions inside an image. That means this region is having some texture which are repeated many number of times, and this is also having texels that are repeated many number of times here, because the repetition may be periodic or it may be aperiodic. So both region based methods and boundary based methods have been attempted here to segment the texture images here, take the texture inside the image. Okay. The next part in the analysis, that is texture analysis, is shape recovery from the texture. So this texture is present inside an image. So I have provided with an image here. Can I able to recovery, or can I able to recognize what can be the shape of an object that is present inside an image, right? So for which, how these textures are helpful in order to solve out the issue, that is how can one able to recover the shape from the given object that is present in the image. So image plane variation in the texture properties, like I have here. So inside this image I do have yes sphere. It resembles me, like it gives me a look of a circle. This gives me a look of some kind of a four sides, right? It is having 1 2 3 4 5 1 2 3 4 5, some kind of a parallelogram. Okay, and this is giving me some shape, but all these three objects inside this image giving me a 2D view. Okay, so based on this image character, I can able to find out what its shape may be. Like, is this a sphere, or is this a cube, or is this some kind of a cylinder in shape? So how one can able to find out the particular shape from the image, right? So image plane variation. So if it is a square, I can simply say that it is a two-dimensional square. But this I have here image plane variation, because as soon as I have been provided with this image is like I can perceive this object is having plane variation. That means this is one plane I can feel, this is one plane I can feel. So in this manner, some plane variations also I can feel. Like this one, you can see this plane is spherical in shape, and this plane is some kind of a like a rectangle in shape, and this plane I can feel it is a spherical in shape. How I can able to feel so and so plane variations? It all depends upon the density of the texture here. Like you can feel the black this area, the texture density is very small when I compare my texture density at the top of this face, because this is one face, this is one face, right? This is one plane, this is one plane. So this is my top view and this is my side view. So I can easily analyze that this, because of these plane variations, I can feel that it is in a shape of, or it is a structure of a cube. So based on the texture density and size and orientation, I can these are acting as a cues. Okay, these are acting as a clues such that I can exploit what will be the shape of the given object or of the given region that is present inside my image. So you can see here, if you consider this as an example, I do have here more size of the texture. So as you go on nearer to the boundary of this region, the texture size is getting shrinked or compressed, and as you go on along the diagonal or along any vertical or horizontal axis of this region, so dynamically the shape or the size of this black texture is getting compressed. So it is indirectly giving me a feel that it is resembling a structure of a sphere here. Okay, the same thing you can see, and also the density of the texture is also getting shrinked here. Size is getting shrinked, and even the orientation also, because like if you see here, I can feel here a complete square, but here the square is some bit like there I feel some kind of a tilt the square had undergone, and it is also undergone more tilt here and more tilt and more tilt. So tilt is there, as well as there is a change in the size, and as well as there is a change in the orientation. So by using these three as a parameters or as a hint, I can easily exploit what can be the shape by using these textures. So this is the shape recovery from the texture one can do. That means texture analysis can be done, by using which one can able to recover the shape here. The same thing you can see in this object also. And the next one is the texture synthesis. What is this texture synthesis? This synthesis is nothing but it is the process of constructing a large image or a large texture from a smaller or micro texture here. From a small digital sample image, I will be taking here into consideration where I can develop a macro texture here. This is nothing but a texture synthesis. That is, it is the process of algorithmically constructing a large digital image from a small digital sample image by taking advantage of its structural content. So by this structural content, I can able to produce a larger structure here. So this is a texture synthesis. Now how to define exactly a texture? So we do have here two approaches to define a texture. So that is a structural texture. Here a texture is a set of primitive texels. Like a image is having a pixels, in the similar manner a texture is having a texels here which are acting as a primitive elements. So these texels are repeated in regular or repeated manner, right? So when the size of the texture primitive is very large, first we have to determine the shape and properties of the basic primitive. So if this you take this one brick pattern, this is, so when the size of the texture primitive is large, first determine the shape. So this is the shape and the properties, because if you take this one, this is my shape, right? So this is my shape of a brick. So the shape and the properties of this primitive, that means this texture basic properties like shape and properties and the rules which govern the placement of these primitives, that form a macro texture. So this brick pattern, whenever they are repeated significantly many number of times, they form a macro texture here. So what is the primitive here? It is a brick pattern. The same thing you can see here in this image. So by this brick pattern, inside it I have to determine what is in the shape and what are the properties of this basic primitive. So the shape of this texture is rectangle, and what are the properties of this basic primitive, that is what is the texture properties I need to find out. So this is the structural definition for a texture. And so what is this statistical definition is, a texture is a quantitative measure of the arrangement of intensities in a region. So this set of measurements is called a feature vector. Statistical methods are particularly useful when the texture primitives are small, resulting in a micro texture. So the statistical texture, the perfect example I can give here is a close-up pattern in the bricks. So this is a brick, right? So whenever I zoom it inside, zoom in, so close-up pattern I will be getting here. So where once I zoom this brick, I can able to form here a statistical texture. That means it is a measure of the arrangement of intensities in a region. So how all are the intensities in these textures are like arranged. So if I zoom in any of the brick, so all the bricks are nothing but these are the textures that are repeated many number of times. Finally I have got here a macro texture. But inside it, inside this structural thing, I do have a statistical characteristics. That means for which I need to take one brick into consideration, and once I go deep into the brick, I will be getting a statistical. That means, so you see here, it is the arrangement of intensities in this region, in this texture, how the texels are arranged, and what is the intensities of the texels in this region, in this texture. Okay, so by which I can able to produce the feature vector, like how pixels are, by using the pixels how one can able to produce the feature vectors, and by using the texels also one can able to produce the feature vector. Thereby I can find out some statistical measures from it. Okay, so this is my micro texture. Okay, this is how one can define the texture here. Statistical is this one and structural is this one. Okay, so the statistical or the spectral techniques are used for the texture representation, that is fine, but the statistical movements can be computed only by the image histogram. For example, you take here, I do have here an image. Okay, these all are the images. So a image here having 50% black and 50% white distribution here. The same thing you can see in this image and also in this image also. So these three images are having same intensity distribution. That means 50% white distribution and 50% black distribution. These three images are having, but the textures are different here. So here you can see the black box is a texture, here white box is a texture. So this black box is repeated in this manner, the white box is repeated in this manner. So finally I am having 8 number of black boxes and 8 number of white boxes in this image, which are repeated one after the other. But coming to here, of course I do have 8 number of black and 8 number of white boxes, but white boxes, after the completion of alignment of all the 8 white boxes, I will be having 8 black boxes. Okay, so that means vertical alignment of white boxes. After that one, we do have here vertical alignment of all the black boxes here. Okay, and coming to the third image, so horizontally first I will be aligning or assigning all the 4 white boxes. After that one, next black texture is repeated, next white texture is repeated, next black texture is repeated. So I do have here different pattern of textures. Okay, so of course the 3 images are having the same intensity distribution, but the textures are different here, because it is black white, it is half white, next half black. So it is 1/4 of white, next 1/4 of black, next 1/4 of white and black. So of course finally I am going to yield the same histogram for the 3 different textures or the images. Okay, so a simple 1D histogram is constructed in this manner, but it is not useful in characterizing the texture. Why? Because as in this figure you can feel the 3 different images are giving me the same histogram, by which I can able to find out the metrics from the histogram, like mean, median, standard deviation, skewness, and number of bin size, and many number of metrics I can able to find out from this image here. And the above image, these 3 images are having the gray levels or the intensity levels same. That means same intensity distribution, but different arrangement is having in its texture, but they are producing me the same histogram. So because of having same histogram, I cannot use for image texture analysis here. I cannot perform the image texture analysis perfectly. So that is the problem with the statistical texture descriptor is it fails in distinguishing the 3 different images, because like the statistical texture descriptor I can able to find out the image histogram, but the image by based on or completely depending on the image histogram, I cannot able to find out, or I cannot able to distinguish my image here. Okay, so if this is being given me as an input, I don't know what accurately my input image is, this one or this one or this one. So at this point the statistical texture descriptor by which I can able to find out a 2D histogram, so this concept fails. That means I cannot able to correctly tell what the input image is, this one or this one or this one. So at this time, so how to overcome this problem? That statistical measures described so far are easy to calculate but do not provide any information about the repeating nature of the texture here, right? So to overcome this one, we do have here a GLCM, that is gray level co-occurrence matrix, that is based on the study of statistics of pixel intensity distribution. That is how the pixels are distributed. So a GLCM contains information about the position of pixels having similar gray level values. So here histogram I cannot able to find out what is the position, but this GLCM is containing the information about the position of pixels having similar gray level values. Okay, so what is this GLCM? Let us have a look inside it. So this GLCM, that is gray level co-occurrence matrix, or it is also referred as a co-occurrence distribution, which is a two-dimensional matrix here, that is denoted by P. So an image is generally composed of pixels with intensity levels. So a GLCM is nothing but it is a tabulation of how often different combination of gray levels occurs in an image or a image section. So for which let us take an example of here. I will explain this GLCM how to find out. Okay, for any image you take into consideration. So for any image I can able to obtain the GLCM. So how this GLCM works and how it is useful for the classification also we'll discuss. So GLCM here is counting all the pair of pixels that are separated by D. Actually this GLCM is nothing but it is a matrix of n cross n. Of course I didn't kept the thing here in the slide. Okay, yeah, let's take this one. So I do have here an input image. This input image is having 5 cross 5. The size of this input image is, so I need to ultimately find out the GLCM from this input image. So the GLCM matrix size will be n cross n. So what is this n here? This n is nothing but it is the number of gray levels that are present in the image. So by seeing only I can feel there are 3 different intensity levels present in the image, right? So the size of the GLCM will be 3 cross 3 square matrix it is. So this GLCM is computed by using 2 parameters here. Okay, so this is my 5 cross 5 image, right? The GLCM will be a 3 cross 3 matrix. Why? Because I do have here 3 intensities. The same thing I have obtained here. So how to find out this GLCM matrix? So this GLCM is computed by 2 parameters. One is small d. Okay, you can see here displacement vector, or this small d is nothing but it is the relative distance between the pixel pair. If suppose if I is 1 pixel and j is 1 pixel that are present inside the image, so the difference or the relative distance between this I and j, which are nothing but the pixel pair, is nothing but the displacement vector, that is small d. In fact, it is the relative distance between the pixels pair here. And along with I do have here theta. So this theta is nothing but it is the relative orientation or the angle. Like how this I and j, how they are in straightly connected, or they are diagonally connected, or reverse diagonally connected. So based on this theta also one can able to obtain the GLCM matrix. That means the GLCM is computed based on 2 parameters. One is relative distance between the pixel pair I and j, and what is the relative distance, and next is theta, that is relative orientation between the pixel pair. So assume this is a box. So like I have here a pixel, I do have here a pixel. So these 2 pixels are connected with an orientation of 0 degrees. And this I have a pixel here, I do have a pixel here. These 2 pixels are connected with an orientation of 45 degrees here. So and these 2 pixels are connected with an orientation of 135 degrees. So if the pixel to pixel difference, if I take city block distance into the consideration, so this pixel and this pixel, they are separated with 1 unit as a displacement. Okay, so in this manner one can able to obtain the GLCM, that is gray level co-occurrence matrix in the image. Okay, next, so that means, can I say there are 8 directions of orientation here? Okay, that means 8 directions, that means from 0 degrees 30, 45, 90, 135 up to 8 direction there will be orientations between pixel pair here. So one pixel and other pixel are related with 8 different orientations. Okay, let us take this one as an example. Let's come to the point straightly. Now this is the input image. The input image is having 3 different intensities, 0, 1 and 2. So 3 means I can able to construct 3 cross 3 GLCM, that is gray level co-occurrence matrix here. Since there are only 3 gray levels, the GLCM is denoted with P as the representation. So this P indicates it is the GLCM, that is of 3 cross 3 matrix. So I and J are nothing but these are the pixel pair. Okay, now so this GLCM capture properties of a texture, but they are not directly useful for the further analysis also. So like before going to elaborately explain this point, let me find out the GLCM, how one can able to find out the GLCM from the given input image. So let D equal to 1, 1. This is my pixel pair. Okay, so now P of 1, 0. So how this is P of 1, 0, and this is 1 is I, 0 is J. That means first pixel is nothing but it is I, second pixel is nothing but it is a J pixel, which are displaced by D units. Okay, so P of 1, 0 is nothing but the first pixel is 1, the second pixel is 0. So 1 and 0, how they are displaced by the orientation? So the orientation is diagonal orientation, and how they are of 1 unit distance as given in this. Okay, let me take D as 1 unit distance, city block distance I am considering. So P of 1, 0. So by seeing this input image P of 1, 0, what? So this all the blue wrapped curves, so all the blue curves in this image, like 1, 0, first pixel is 1, second pixel is 0, here also first pixel is 1, second pixel is 0, and how these 2 pixel or how the pixel pair is related or oriented in this diagonal. So 1, 0, and here also 1, 0. That means it is of some kind of 45 degrees orientation. 1 and 0 are related with each other with 45 degrees of orientation, and they are separated with each other by 1 unit of city block distance. Okay, and if you take P of 2, 1, the I pixel value is 2 and the J pixel value is 1. So by seeing this image, I is 2 and J is 1. So how many number of occurrences I do have here? 2, 1 here 1 time occurred, 2, 1 second time occurred, 2, 1 here third time occurred. Okay, by seeing this one I can able to construct my GLCM, that is gray level co-occurrence matrix. So P of I, J GLCM. So I do have here I number of rows, J number of columns. So this is I, this is for 0th row, first row and second row, 0th column, first column and second column. So P of I, J, P of 0, 0. So P of 0, 0, anything is there that is of diagonal matching? No, because 0, 0 nowhere I do have a diagonal, that means 45 degrees alignment matching nowhere. So what is this 45 degrees alignment means? So let D equal to 1, 1 I will be taking. Okay, that means I am moving 1 pixel right and 1 pixel down. Okay, that means if it is p of 2 comma 1 is there, so p of 2 comma 1 means 1 pixel right and 1 pixel down, so 45 degrees of orientation. That means angular, you say it is angular displacement or some kind of a orientation with 1 pixel with other pixel is making. So 1 pixel right and 1 pixel is left in this manner. Okay, the same thing you can see here. I will explain this slide. So p of I comma j, p of 0 comma 0, nowhere, no diagonal here. So p of 0 and 1, p of 0 and 1, anyone is making here 0 and 1. Yeah, this is making one occurrence, and here also 0 one more occurrence. So the value is 2. And p of 0 and 2. So first pixel is 0, second pixel is 2. 0 and 2, how many number of times? This is first occurrence 0 2, and yeah, here also 0 2, this is second occurrence, so 2. And similarly I can able to find out all the elements for the GLCM, which is of tree cross tree matrix. So the elements of the GLCM can be normalized here. So why we have to do the normalization is, the GLCM basically it is not a symmetric matrix. Since the number of pairs of pixels having gray levels I comma j may not be necessarily equal to the number of pixel pairs having the gray levels j comma I. That means I comma j may not be equal to j comma I. So to overcome this one, the elements, all the elements of this GLCM are to be normalized. So how to perform the normalization is simply by dividing each entry by the total number of pixel pairs here. So 0 plus 2 plus 2 plus 2 plus 1 plus 2 plus 2 plus 3 plus 2. So if I do all the elements, if I do the sum, if I perform the sum, I will be getting here 16. So each and every entry of the GLCM is to be divided with the summation of all the elements. I will be getting the normalized GLCM. So this normalized GLCM or the normalized co-occurrence matrix, where all the elements will be having the range in between 0 and 1. And so it giving me a dot as a probabilities, like, and so let me take this one as an example. I will explain you this with by taking into consideration one example in the next upcoming slide. So this will be my normalized GLCM. So this is mainly performed as the GLCM is not a symmetric matrix, and the number of pairs of pixels like I comma j gray levels may not be equal to the pixel pair j comma I. So to overcome that one, I am doing here normalized GLCM. So for uniform textures, like you take here, I have here 1 comma 1. So d equal to 1 comma 1, such that this one is white. Okay, 1 or like 1 represents it is white pixel, 0 represents it is a black pixel, right? Okay, so these are the GLCM matrices. Now what I am doing here is, it is my chessboard actually. So this is my chessboard, and the displacement is 1, and the direction is in this manner, diagonal direction. And here the displacement from I to j is in this manner, and the direction is 0 degrees. Okay, now so I need to consider here the diagonal. That means I comma j pixels are connected with each other in this way. That means moving right and coming down, right? So in this diagonal, and I and j are related with each other in this manner. So just moving right. Okay, no coming down, no diagonal here. So so PD of I comma j, so this is 0th element first element, 0th element first element, so 0 and 0, so 0 and 0 means 0, so 0 0 0 0 0 0 0 0, how many number of 0 0, that means 0 represents here a black pixel, one black pixel, first is a black pixel and second is also a black pixel. How these two black pixels are related? So how many number of occurrences? So 1 2 3 4 again 5 6 7 8 up to number of 24 number of occurrences I do have here. So I pixel and j pixel, like 0 and 0, I can feel 24 number of occurrences. Coming to 1 and 1, because this is 1 and this is 1, right? So 1 and 1, 25 number of occurrences I do have here in this texture image. And coming to 1 0 and 0 1, I don't have any white pixel which is connected with black pixel in a diagonal fashion. So that is why 0 and 0 I have written here. These two boxes are 0 and 0. And coming to d equal to 1 comma 0, that means the first pixel is 1, the second pixel is 0 here. Okay, so that means the scenario you can see here, observe here 1 and 0, because 1 and it is 0 at column, or because if this is j, like how you have seen, this is j and this is I, 0th row, first row and second row, because these all are the first pixels, these all are the second pixels. So the second pixels and the first pixels. So first pixel is 1, that means here 1, second pixel is 0, that means this 0. So the first pixel and the second pixel are related with each other in a horizontal direction. So the angle will be 0 degrees. So 1 and 0, white and black, white and black. So these two form a pair, these two form a pair, these two form a pair. So how many number of occurrences are there? White and black, white and black, white and black. So there are in total 28 number of occurrences, 1 and 0. And coming to 0 and 1, 0 and 1, 0th row, first column. That means 0th is the first pixel, first is the second pixel. 0 comma 1, PD of 1, 0 comma 1, that is white and black. Black and white. So black and white, black and white, black and white, black and white. So 28 number of occurrences are there. So finally I can able to obtain my GLCM matrix for the checkerboard is in this manner. Okay, so that means the GLCM for this one is that is d equal to 1 comma 1 is this one, and for d equal to 1 comma 0 is this one. So this d equal to 1 comma 1 is nothing but I have to move right side 1 unit and I have to move downside 1 unit. Here d equal to 1 comma 0 is nothing but I have to make a move 1 unit right side, and there is no need to move any units down because it is 0. So the pictorial representation for d equal to 1 comma 1 is this one, that is diagram, and for d equal to 1 comma 0 is in this manner. So here I am considering only 1 unit distance only. Okay. So for uniform textures in this manner I can get the GLCM. So the GLCM captures properties of a texture, right, but they are not directly useful for further analysis because I just obtained my GLCM, that's it. But I have to do something here, that is I need to perform the classification, right, of the regions in the image. So what is the object that is present in the image, so that I need to perform means the GLCM capture properties of a texture but they are not directly useful for further analysis, such as the comparison of two textures. Okay, so like in the given image I may have a cat, or I may have a black, or I may have a dog. So the dog and the cat are two different textures. So if I have given one a testing texture, and I need to categorize is that texture belongs to a dog or it belongs to a cat. So how to do that kind of analysis is, we will see now. So the GLCM cannot directly use for the further analysis, but the numeric features, which is nothing but the second order statistics, are here are computed from the GLCM matrix that can be used to represent the texture more compactly. So let us, how it is happening, we'll see. So by the GLCM we can able to get many number of numeric features like entropy, second movement, contrast, correlation, variance, homogeneity, mean, dissimilarity. All can be traced from the GLCM matrix. Okay, from this GLCM matrix one can able to find out all these parameters. So what is this entropy? So the entropy is nothing but the entropy measures the occurrence of random pair of pixels. So for each and every second order statistics, I do have here the definition. So by using this one can able to do the classification. So what one can able to find out what the texture is exactly, right? So like energy, entropy, homogeneity, inertia, correlation, shade, variance, all like the respective formulas are this one. So the what will be the maximum probability. So the probability is nothing but the maximum probability is nothing but like the normalized GLCM. I will be having the range for each and every element in the normalized GLCM in between 0 and 1. So that means they are the appearance of all the elements will be in the probabilistic manner, right? So what will be the largest entry that will be giving me the maximum probability? And coming to here, I can determine the following parameters once I get the normalized GLCM, right? Like for example, you take contrast. So what is this contrast is doing here? So it is a measure of local variations like a image is having. So a measure of intensity contrast between a pixel and its neighborhood over the entire image, that is a contrast. So if there is a large amount of variation in the image, so definitely the GLCM will be concentrated away from the diagonal and the contrast will be very high. So all these things I will explain you by taking a example. So this is my given input image. I need to find out my co-occurrence matrix such that the direction is 1, okay, and theta equal to 0 degrees, and let me have the displacement vector as 1 unit, that is d equal to 1, 0. So d equal to 1, 0 means horizontal direction, right? So 0, 0, how many number of occurrences? 0, 0, 1 number, here 2 number of occurrences, so 0, 0, 2. And coming to 2 and 2, you take this as an example, 2 and 2, how many number of 2 and 2 are there? So in this horizontal direction, that is d equal to 1, 0, because you have seen here d equal to 1, 0 means this kind of alignment. So I and j, they are related horizontally with 1 unit as distance. So 2 and 2, 1 number of occurrence, second number of occurrence, and third number of occurrence. So how many number of occurrences in total? 3. In the similar manner I can able to find out, because I do have here 4 intensity levels. So 4 cross 4 GLCM matrix I can able to find out. So the GLCM matrix finally I will be obtaining in this manner. So I can able to find out the normalized GLCM for further analysis. So we have here, if I sum all the elements in the GLCM, I will be getting the sum as 12. So normalized GLCM is occurred such that each and every entry in the GLCM is divided by the summation of all the elements occurrences. So that means 2 by 12, 2 by 12, 1 by 12, 0 by 12. So 2 by 12, 0 by 12, 0 by 12. Okay. So all the things, if I do the mathematics, I will be getting the normalized GLCM in this manner. That means each and every element is in the probabilistic appearance, right? So that means each and every element are in between 0 and 1 range, right? Where among all these elements the maximum probability is 0.25. So as this is my largest entry in the matrix, and it is my strongest response in this normalized GLCM also, I can able to say. Okay, now so parametric calculations I need to perform, because I need to evaluate what are the second order statistics, right? So the maximum probability is 0.25. And what is this contrast? So the contrast is given by summation I minus j whole square into Pij. So this Pij is nothing but it is a normalized GLCM value for particular I and j element. So Pij means, for example, if you consider 0th row and 0th column, so this is the one what you are going to obtain. So P of 0 and 0 means, so I is 0, j is 0. So substitute 0 minus 0 whole square into Pij. P00 value is how much? 0.1666. So that means, as I have, it is a 4x4 matrix, definitely I do have here 16 number of elements or 16 number of cases I need to find out, for which contrast I need to find out for the entire GLCM. So 0 minus different occurrences. So I will be getting the value of the proper substitution of I and j values. 0.588 is the contrast for the given texture I can able to obtain. So this contrast is nothing but it is a measure of local variations that are present inside my image. So in the GLCM will be for example, it is the contrast is nothing but it is just like a measure of intensity between a pixel and a neighboring pixel over the entire image. So if there is a large amount of variation in the image, means the GLCM will be concentrated away from the main diagonal, and the contrast will be very high here. So this is about the contrast calculation. And coming to uniformity, so what is this uniformity? It is given mathematically in this manner. So it is a sum of squares of every probability in the normalized GLCM matrix. I will be getting here the value 0.1665 after proper substitution. Okay, it is a measure of uniformity that will be in the range of 0, 1. So uniformity will be 1 for a constant image, and it is highest when all the elements are of equal. So this is about uniformity. And the next one is homogeneity. So the homogeneity mathematically is given by Pij by 1 plus I minus j in magnitude. So module I minus j. So homogeneity of a image, a homogeneous image will be result in co-occurrency matrix, which is a combination of high and low. Okay, where the range of gray levels is small here. The GLCM will tend to cluster around the main diagonal. So this is the character of this homogeneity, and the entropy can be traced out like this: P log of P. Actually it is P log of 1 by P. So I have taken log p means minus will be coming, because you know how to find an entropy, right? So entropy is nothing but it is a measure of information content, like the measure of randomness of intensity distribution. And the entropy will be highest when all the entries in the GLCM are of similar magnitude, say, and it will be small when the entropies are unequal. Okay, that means when the elements are unequal, the entropy will be small here. And coming to the mean, so how one can able to find out the mean? So if mean is obtained means I can able to find out the standard deviation, right? So mean MR equal to sigma I equal to 1 to k ith element dot, that means it is a multiplication, sigma j equal to 1 to k pij, that means probability of ith element and jth element, ith and jth, that means ith row and jth column particular element, what is its probability. Okay, in this manner I can able to obtain the mean and also the variance. So variance, how to find out this variance? So variance is nothing but the standard deviation, and this is the formula, sigma I equal to 1 to k I minus mr whole square. Mr is nothing but it is the mean of all the rows, right? And similarly ij minus mc, mean of all the columns whole square into pj. So these are the movements. Okay, first movement, second movement we have here, right? So this is standard deviation, and next is correlation. So correlation is nothing but it is a measure of linearity, image linearity. So correlation will be high if an image contains a considerable amount of some linear structure, and the mathematical expression for this correlation is I minus ith element. Okay, so substitute the value, because I do have here 0 1 2 3 as the I values, and 0 1 2 3 as the column values. So I minus mr is nothing but it is here mean of all the rows and mean of all the columns into probability of each and every row, that is pij is the element in the GLCM, normalized GLCM matrix, and this is my standard deviation sigma r, and this is, sorry, it is rho r, and it is sigma c. So in this manner I can able to obtain all the second order statistics from this normalized GLCM. So after which, so these all are the second order statistics and the corresponding formulas. All these are the corresponding formulas. Mean and variance, sigma is nothing but it is the variance, right? So say this what do you say, I can able to find out all the second order statistics. This is this is the example, so by which one can able to find out what the texture that is present in the testing image, and by doing the comparison one can able to find out or classify what the object that is present inside the testing image. So in this manner the GLCM is highly helpful in able to recognize the given texture that is present in the image by finding out the second order statistics from the like which can be find out once I have obtained the normalized GLCM. So in this manner the texture is defined. So by using the texture the GLCM can be traced out, and one can able to compute the given one can able to compute the second order statistics, and one can able to find out what exactly the texture is, right? So for now we will end the session. And thank you and have a nice day.